start. Hello and welcome back to Calculus 1, section 4.4 on graphing functions by hand. Right? So no calculator, no graphing calculator, no Desmos, or your other graphing utility. You guys get to learn how to sketch a graph of a function. And what we are going to do is we are going to do this using calculus rules that we learned so far. This is what I call a shopping list, right? Because we are going to have, I don't know, 10 to 13 bullet points, whatever it works out by the time I'm done. So this is your list of things to calculate. And then you look at these things and you go. So number one, we need to very conscientious of domain. We must know the domain, because you are not going to waste time working your first derivative test in a region that doesn't exist, right? So that's one thing. So we need to know the domain. Range, we don't need to know the range, so we can skip over that one. Now, number two, let's go with the algebra calculations for X and Y-intercept. So X-intercept and Y-intercept. Intercept, there we go, there's an N missing. So X-intercept and Y-intercept, I'm going to put in purple over here, set Y to 0 and set X to 0. So these are standard Algebra 1 calculations which you guys did on linear functions and quadratics. Now you're going to do it on everything else. So that's algebra. Number three is going to consist of three different types of asymptotes. We have vertical asymptote, now problem might not have any. You have horizontal asymptote, and horizontal asymptote, and vertical asymptote, horizontal asymptote, and slant asymptote. Now, these are the pre-calculus concepts, but we did learn, right, in the limit chapter, chapter 2, 2.5 and 2.4, 2.5, how to deal with this. So this was your 2.4 section. And both of these were in 2.5. And they were also in pre-calc. Also in pre-calc with K's. There we go. So we're going to do the, so we get the domain, that's from pre-calculus, then we have X and Y intercepts from algebra, then we have vertical asymptote, horizontal asymptote, right? Then I'm going to see over here, bullet point 4, get first and second derivatives. So get f prime and get f double prime and box them, because what follows next are first and second derivative tests. So number 5, first derivative test. Now, by the way, since I'm specifying everything, this is chapter 3, right? Because your derivatives could be product rule, quotient rule, chain rule, logarithmic, right? Any of that stuff goes. So find first and second derivative test. And then first derivative test, that was previous section 4.3. And we have number 6, do the second derivative test. Now please remember, that for these, right, you have those long calculations and they give you min and they give you max and they give you increase, decrease, concavity, inflection points, right? So they're going to give you a lot of information for you to graph. Guys, when they give you critical points, those are points on a graph, right, through which the line goes. You will be graphing those points, and then you will snake the line through those points. So if you have X-intercept, Y-intercept, inflection, critical points, asymptotes, right, you put all of that stuff in a graph, and then you just get to snake the line through the points around the asymptotes, right, and you will be able to get this done quickly. So we have the first and second derivative tests. 7. I'll write symmetry, but we pretty much never use it. So I just want to have a complete list. We don't usually use symmetry for anything because we end up having so much information that symmetry pretty much never plays a role, but it is a mechanism that we can utilize. Number 8 is calculate or compute additional points. Compute additional points. That's pretty cool. You literally pick x's and compute y's, right? If there is a region where you are not sure which way the line would go, all you need to do is to compute extra points and you are, you're good to go. Number 9, graph and win. There you go. Wow. That's a lot of stuff before you get to this point, right? It's a lot of stuff. I promised 13, right? So 9. If you do these little parts, right, each one separately, so you do get 13. Yeah. Is it 12? All right. 12 steps. All right, fine.
And win.
The celebration at the end. Should I put cake instead? No. Calculus cake. Yes. So this is the shopping list. And now we get to use this on an example. Let's say you don't know what the graph of, you should know what the graph of 1 over x squared looks like. You're in Calc 1. But let's say you don't. So graph f of x equals 1 over x squared. We have our shopping list. Number 1, domain x is not allowed to be 0. So you can either write it that way, or you can write it as negative infinity to 0, union 0 to infinity. This is important because if you end up with a critical point at 0, can 0 have a critical point? No, because if you plug in 0 in original equation, right, the whole thing explodes. Number 2, x and y intercepts. Okay, so for x-intercept, I get to set y equal to 0. So 1 over x squared equal to 0. When I cross multiply, I get x equals 0, which cannot be. So no x-intercepts. For y-intercept, I set x equal to 0. So I get 1 over 0 squared equals to no solution, because you're dividing by 0. So no y-intercept. Number 3, vertical asymptote. What we clearly know that there is one at x equals 0. Do we? Look at the domain. What did we learn in pre-calculus? We learned that if you set denominator equal to 0, you get your vertical asymptote. So there is a vertical asymptote there. I'm boxing this important information. Horizontal asymptote. Is there a horizontal asymptote? Well, if you remember your section 2.5, you are supposed to take the limit as x goes to infinity of 1 over x squared and see what shows up. So what is 1 divided by infinity? 0. Very good. So we have horizontal asymptote at y equal to 0. That is also a piece of information that we are going to use. Now, slant asymptote is mutually exclusive to horizontal asymptote. You can't have both, one or the other. So, no sa, because we have ha. I'm serious. You can have neither. You can have one or the other, but you definitely can't have both. That's the rule. That's the deal. Number 4. So we got all of our asymptotes, right? We tried all 3. We got 2 out of 3. That's great, right? The most you can have. Well, you can have multiple vertical, right? And now, at number 4, we are supposed to take our first and second derivative. Oh, that's where the 13th calculation is. I didn't put the separate line. That's where I remember that the lucky 13 was there. So for number 4, we are just going to find the first and the second derivative. And we now need f prime of x, which would be the derivative of so we are taking the derivative of 1 over x squared, which you can write as x to the negative 2. So this is negative 2x to the negative 3, which is negative 2 over x cubed. And for the second derivative, you are going to look over here and have a 6x to the negative 4. So you have 6 over x to the 4. So f prime of x is negative 2 over x cubed, and f double prime of x is 6 over x to the 4. I boxed this because I need them, right? You are not graphing these, but I have to box them. Maybe I box them orange or something, or blue. Let's box them blue. Because now in number 5, I get to do first derivative test, f dt. So now we know what to do. We set our derivative equal to 0 to find horizontal tangencies. So that was last class. So negative 2 over x cubed is equal to 0. We get negative 2 equal to 0, which cannot be, which means no crit points. Now that immediately means no min max. That's very important. But then you know that for the first derivative test you are supposed to partition, right? And we have a vertical asymptote, so we will partition at the vertical asymptote 0. And as we did last class, we will choose 2 test points, negative 1 and 1, let's say, to be lazy. And then we'll find our first derivative, right, at negative 1. The first derivative is given as negative 2 divided by negative 1 cubed, which is 2, which is larger than 0. And I have immediately increase, actually arrow up. I should put increase over here. There we go. Then I calculate the first derivative at 1, which is negative 2 over 1 cubed, which is negative 2, which is less than 0, which is decrease, and I put the arrow down. Obviously, you cannot, and I said obviously, you cannot claim maximum at 0 because there are no critical points. We have a vertical asymptote at 0. No critical points going through x equals 0. Therefore, we can't claim max, even though it looks like there should be a max. We are done with the first derivative test. This is all I need, right? I need to know when the function is increasing, when is the function decreasing. Do I have to write the sentence answer? Well, on the test, yes, when you just have a question that says, do the first derivative test. But now, it's graph a function. So you just need to use this information here to draw the function. So you don't have to write sentence answer here. But if it's a standalone question, you have to write the... All right, 6. Second derivative test, SDT. Our second derivative boxed was 6 over 4x to the 4. We set that equal to 0 to find inflection points. When we cross multiply, we get that 6 is equal to 0, which is not. So that immediately means no inflection points, which immediately means, oh no, that's it. No inflection points. But we still have a vertical asymptote at 0, so we get to partition at 0, right? Our domain from negative infinity to positive infinity. And we pick 2 test points, -1 and 1, and then we do our second derivative test. So f double prime at -1 is going to be 6 over -1 to the 4th, which is 6, which is larger than 0. It's concave up. And second derivative at 1 is 6 over 1 to the 4th, which is again 6 larger than 0. So concave up, everywhere concave up. And you know what? I have enough information. I hope. Let's see. Remember, I am always allowed to calculate additional points if I need to. So let's draw the graph. You put your x and a y coordinate system, and immediately we know that we have a vertical asymptote in red and a horizontal asymptote in blue. So red line is x equal to 0, blue line is y equal to 0. So that's your ha, and this is your va. Vertical asymptote, horizontal asymptote. Now, having this immediately sets some things in perspective here. Guys, I can only draw this or that. Do we all agree? Because these asymptotes, right, they just cut the space in 4. So if I have to draw a function to the left of the red vertical asymptote, I can only do the top pink or the bottom pink shape. Now, when you are looking at these two pink shapes, and they are both to the left of 0, this is where these tests come in. Do you see how to the left of 0 you have increase and concave up? Which piece is increase and concave up at the same time? Second quadrant, the top one, right? This is concave up and increasing. The one on the bottom is concave down and decreasing. So, kill that one. The same thing happens on the other side. I get to draw this or that. We go back to our tests, and the test is asking for decreasing and concave up. Which one is decreasing and concave up?
First quadrant.
The first quadrant, the top, right? Decreasing, right? If you are walking to the right, you will be walking down, right? So that's decreasing. The y values are getting smaller. And it's also concave up, right? If you complete it into a U shape, it holds the water. That's what a concave up means. Now you can have only one side of concave up. It's okay. So that's a concave up. This one is again concave down. This one is increasing, right? So it's completely opposite of what we need. So you kill the bottom one. Great. Now, in my time, when I took calculus, I would go to my trusty graphing calculator to check my answer, right? You guys have access to Desmos. So you go and you type this function in Desmos, and Desmos will immediately graph. So you have 1 divided by x squared, and there it is. This is exactly what we have on our graph. And you see there are no min, no max points, no changes in concavity. We don't have any X-intercepts or Y-intercepts, and they're following these asymptotes. Okay, so we'll actually run into that. So, cool. Let's do more, because we can. Remember what we want to figure out: ln x squared, sine x squared times sine x, right? All of these cool things. We get to warm up with vanilla stuff. Okay, it's beautiful problems over here. 1 over e to the negative x minus 1. They pull this stuff. So this is what your problems look like, and they just say graphing functions, go. For each one of these problems, you get to do the whole list of things, which is why I say it takes a very long time to do these problems. So what do you do first, right? Before you go to the problem, warm up your joints, right? Because this is one of those sections that it's amazing for killing time and developing carpal tunnel if you don't already have one. 27 is cool. I like it. X minus 2 root x. Graph by hand. X minus 2 root x. Again, I have nothing new to teach here. We just need to worry about, drawing the function when you have all of the information. So problem 27, f of x is equal to x minus 2 root x. Domain. Number 1 is domain. What's domain of x? All real numbers, right? Domain of x, all real numbers. You can plug in any number for x, and it's good. What's the domain of square root of x? Greater or equal than 0. Good. So now we have a conflict over here. One part of the function has domain for all real numbers, and the other part of the function has 0 and up. What is the overall domain for the entire function? Greater y.
Because it's a restrictive.
It's a restricting, yes, it's the restrictive one. So this one over here is all real numbers, and this one over here is 0 to infinity, and our overall has to be the one that it's more restrictive. Now, I actually have, if you don't understand that, here's what we have. You are trying to catch a train, right? You're trying to catch a train. Train is leaving slowly. The doors are still open for some reason. If you run, you're going to catch that train. Who's with you? Yeah. You are going to be a nice person and miss the train, right? So you can move as fast as she does, right? Or as you are buying the computer, your computer is as fast as the slowest component. When you have a chain, your chain is as strong as its weakest link, right? Because as soon as you put more weight than the weakest link can withstand, the chain is going to snap. I don't care that other 10,000 links can hold the weight 2 or 3 times more than what you put. As soon as that one link fails, the whole thing falls apart. So, for the domain, you have to look for each piece. The one that is most restricted is the one that is going to dictate across the board, right? Can I plug in -7 for x? Sure. Can I have -7 under the root? No, right? So -7 out of the gene pool, out of domain. So so domain is going to be 0 included, right? 0 included because square root of 0 is 0, so that's all cool. And then we go all the way to positive infinity. Now, guys, when we start partitioning for our first and second derivative tests, we start at 0 to positive infinity. There is no reason for us to check any of the negative numbers. There we go. Great. Let's go with number 2, y-intercepts. X-intercept, set y equal to 0. And you have to solve the equation x minus 2 root x equals 0. In which way we solve this? Well, we say x equals 2 root x, right? You move the root x to the other side. Square both sides. And you get x squared is equal to 4x. Now, you move 4x back to the other side so you can factor. And you have x equals 0 and x equals to 4. There are 2 x-intercepts, 0, 0, and 4, 0. Remember that you set your y equal to 0, so you calculated x's, so there are your 2 points. You get to plot these points, right? So we want to box those to find them later. Y-intercept, guys, 0, 0 is x-intercept and the y-intercept at the same time. You can only have one y-intercept, and if you have 0, 0 as x-intercept, that's immediately y-intercept, so you can't have any more. Right? Just like Highlanders, right? There can be only one. It's pretty much the same thing. All right. Number 3, VA, vertical asymptote. Do we have any vertical asymptotes? Well, x is a polynomial, does not have vertical asymptotes. Root x has no vertical asymptotes. I do not have any kind of denominator, so nope, none. None. Ha, none. Sa, none. No asymptotes of any kind, because you are dealing with the square root, which is radical function, and polynomial x. So they don't have any asymptotes. Number 4. First derivative is derivative of 1, and derivative of x is 1. And then we have minus. The derivative of root x is 1 over 2 root x. So 2 will cancel 2. And this is our derivative. That's our first derivative. Now I am going to rewrite this as 1 minus x to the negative 1/2, because I need to take a second derivative and I need that form. So the derivative of 1 is 0. Then I copy minus. The derivative of this is going to be negative 1/2 x to the negative 3/2. So this is 1 minus and minus, right? Make a plus, over 2x to the 3/2. So there are my derivatives. I'm going to put them on the side and box them blue. 1 minus 1 over root x, and f double prime of x is 1 over 2 x to the 3/2. And I put blue box. Number 5, f dt we take the first derivative, 1 minus 1 over root x, and set it equal to 0. This is to solve the equation, right? You move root x to the other side. You cross multiply, you get root x equals 1. Square both sides, x equals 1. Aha! Well, that's a critical number. And if I have critical number, that could be min or max, right? We are going to do partitioning, but remember, our domain starts at 0, so I don't get to go to infinity. I start at 0, I mean to negative infinity. I start at 0, I partition at 1, and go to positive infinity. This is the reason why you do domain on the line 1. So you don't have to waste your time with things that cannot be. Pick the test points, 1/2 and let's say 2, and then work your first derivative test. F prime of x is equal to, f prime of a half is equal to 1 minus 1 over square root of 1/2. This is 1 minus root 2. If you do the double fraction, and I don't care what the value is, it's just it's negative. The value is negative because root 2 is bigger than 1. I don't care about decimals. Now, the first derivative computed at 2 is 1 minus 1 over root 2. And this will remain positive. Now, we can actually do the common denominator, root 2 over root 2 minus 1 over root 2 is root 2 minus 1 divided by root 2. Again, I don't care what the value is. I just see that I'm dividing two positive numbers. Positive divided by positive is positive. So the top gives us decrease, the bottom gives us increase. And what did I get for free? X equals 1 is minimum, right? See the arrows, the way they go? They go like that. That has a minimum, right? I don't have the y value for it, and I need to plot that, right? So what do? Y of 1, f of 1, whatever. Original function is x minus this, so I have 1 minus 2 root 1 is negative 1, so 1, negative 1, minimum, and that gets a box because I get to plot that also. Why not? Great! Number 6, second derivative test.
Can you do that one more time?
Which one?
The finding the 1, 1. Just plug that into the original.
Yes, because we are looking for the y value.
X equals 1, so you're just finding the y value.
Yes. Remember that y is equal to f of x.
All right. I see.
Right, because you don't get to plug it in at y prime because your points are not x comma y prime. Your points are x comma y, which is why you're plugging in any y value that you have to compute, right? If you have x values, any y value that you ever have to compute always has to go back in original f of x equation because that's the one that provides y. The derivative provides y prime. The second derivative provides y double prime. Second derivative test, we have our 1/2. So second derivative test, we have our 1 over 2x to the 3/2 equal to 0. Cross multiply, you get x 1 equals to 0. So no inflection points. because we didn't get to solve x equals a number, right? No inflection points. And if we don't have any inflection points, what do? Well, we only partition where we have, and that is vertical asymptotes in this case. Now, sorry, no vertical asymptote. We don't have any vertical asymptotes. We don't have any inflection points. So where do we partition? We don't have any.
I thought that was the minimum.
Oh no, this is a second derivative test. I remember telling you that explicitly last time because you're going to run into, very often you're going to run into this where you have no asymptotes and no points. So what do you do with partitioning?
Oh, you just pick random points and see what happens.
Yes, you pick one random point because the entire thing is one partition, right? There's nothing to chop it into smaller pieces, so just pick whatever point you want as a test point. No partitions here. You can write that as a sentence that you don't get to partition because there are no inflection points and there are no vertical asymptotes. So you have nothing to partition with. The whole domain becomes a single partition and you pick any number inside. And you do just that number in the calculation. So f double prime at 1 is 1 over 2 times 1 to the 3 halves, which is all 1 half, which is bigger than 0. It means the entire thing that you are going to see is going to be concave up. Does that make sense to be concave up? Knowing that your critical point is... What was your critical point?
0.
No, what was your critical point? Not location of
Oh,
it.
it's
what?
It's going down. Up.
I said, what is the critical point that you had? Not the location. What is it?
Like the definition out there?
No. It's a minimum. Thank you very much. Your critical point in this problem is a minimum. I'm not sure why was that so difficult. So now, when you have something that is concave up, there's a minimum there, right? You see how nicely this all fits?
Yes.
It's called mathematics. It always works that way. All of the pieces of the puzzle fit 100% of the time. No exceptions, right?
So it's parabola?
Well, let's graph and see. Right? Let's graph and see. What are all of the specs that I have? So we draw the XY the XY graph. The first value we had was 0, 0. Remember that X-intercept? 0, 0? That becomes 0, 0. Then we have 4, 0. So we have 0 and we have 4. Do I have a minimum at 1, negative 1? Sure I do. That's going to be a point. Now, minimum gets a little smiley through it, right? And max gets a frown. I know that there is nothing that lives this way, so I don't have to worry about it. Domain killed the entire thing. You don't have to shade it. I'm just telling you I'm killing the entire region over here. I don't worry about it. So my function begins at 0, 0, right? That's the emerging point. What do I need? I need to start at 0, 0, go through the minimum, go through the 4, and continue going up because the whole thing is concave up and increasing, right? So I go down into the minimum, I turn around to hit the 4, and then I go up forever. It's like a check mark, like a Nike symbol. There you go. What do? You go to Desmos and you ask x minus 2 square root of x, and there's your check mark. How cool is this? Right? You are learning the skill, right, that a $300 machine can do in a second, right? You can do it in 20 minutes. It's called anti-efficiency, but that's what the education is all about, right? But no, in all seriousness, right, in case of a solar flare, all of the technology is gone. There will be only you that can graph these things by hand to bring the society from dark ages, right? Because the solar flare sets us back to 1500s. I mean, just understand that. And one missed us by 9 minutes a few years back, right? So Canada had few years ago, and you can look at this, massive failure of their electrical system. Like the entire country was pretty much shut down. And you know what kind of chaos you had in New York for like 2 hours of no electricity, right? So these flares, they're not a joke. I mean, that's the electromagnetic pulse that actually fries everything. Cell phones, all of the circuits, no trains. You have nothing. We are back in Stone Age. You don't have the pumps for sewage don't work. Your toilets don't work in a house. Your fridge doesn't work. Nothing works, guys. Not having electricity right now is the end of civilization as we know it. It's not like, oh, I'm not going to have TV for 2 hours. No one cares. Just imagine that your toilet is not working. That's just one thing. And in Middle Ages, what did they used to do? A little bucket and then through the window on the street. Like, no, I'm serious. That's what it used to be, which is why the Black Plague killed 2/3 of the population on Earth, because it was unsanitary, right? And then polio and everything else comes with it. So, right? So now going back to this, right, before you say, oh, why I have to do it? Because I can pull my cell phone, well, solar flare can end, right? So now, let's learn how to do these things by hand, just in case of the solar flare. What the chances are, right?
Wear special jackets to identify us as being able to do this emergency. Or sashes.
That's exactly. Your value in the society immediately, goes up if you know these things. You become indispensable. What else is beautiful here? Look at this one, 36, ln of x squared plus 1. I mean, come on. It's simply begging to be worked on. F of x equals ln of x squared plus 1. The importance of this? Hey, nuclear power plant. Shut down, solar flare, right? We got to restart reactors and everything else. What do we need? We need a graph for ln of x squared plus 1. Let's go, right? And this is where you step in. I got this. Let's go. Do some derivatives and, oops. A little pre-calculus aside. Remember the way you find the domain for ln functions?
You set that part
argument.
to 0.
Good. This is called argument. You set the argument.
You do that. You set it to 0.
No,
greater than 0.
Greater than 0. No equal, right? So for domain, we take the argument and we set that larger than 0. That's it. Why? Because the ln graph is only allowed to bring in positive values in a domain, right? That this shaded is domain. There are no x values on the negative side that would bounce into the function and create a y value. So domain is going to be to solve this. Okay, fine. How do you solve this inequality? It's a quadratic inequality. You know how to solve linear inequalities, but this ain't linear. So what do we do?
Can't you use the quadratic formula and just say it's greater than that number?
We are going to use quadratic formula and get complex numbers in this case because it factors over plus minus I. So quadratic formula in this particular problem will not do the trick.
Plus, minus, oh, wait. Oh.
Right, because it's x squared plus 1. X squared minus 1 has plus and minus 1. So guys, how do I find a value that would satisfy this? What x's are satisfying this equation? Anything greater than 0? I would agree. Is there anything else other than that? Everything. Everything. You pick any number under the sun, no solar flare. Any number under the sun. When you square it, what do you get? Positive. Are positive, and then add 1. Right? Are all positive numbers plus 1 bigger than 0? Of course they are, right? All positive numbers without adding 1 are also bigger than 0. Plus 1, they're definitely bigger than 0. So this particular inequality here, quadratic inequality, it works for all x's. So you get to write negative infinity to positive infinity. You can also do the double bar R, which stands for all real numbers. Whichever one you write, I will understand, and others will understand. And you have your domain. You see, so you are used to your ln. You are used to your ln having the numbers bigger than 0 only. But in this case, it's x squared. And that square will take every negative and make it into a positive. So immediately all of the numbers are okay. Great. Number 2. Go. So try to do as much as you can. If you get stuck on any of the aspects of the problem, just skip to the next part, right? First derivative, second derivative test. You should be able to take derivatives. You did chapter 3 test. Not yet. What you did? No, Monday, okay. You're prepping for future. Yes, you're prepping for the inevitable future. I'll let Solar play tomorrow. Let's see. your day. Like, great, now I have to worry about that too. Like earthquakes and other things were not enough. Well, take it this way, at least you don't have to worry about tigers.
My God.
Right? You probably still don't wait for saber-tooth tiger or something like that, but you don't have to worry about that. Oh, bad. It's good.
Oh my God.
Don't worry about it either. So just remember this too.
All right, let's take a look at this stuff. So what about X-Intercept? What do I do? E both sides, right? ln cancels e. We have x squared plus 1. What's e to the 0?
1.
So, x squared is equal to 0, x equal 0. So we have 0, 0. And this is both x and the y-intercept at the same time. So we have a point through which the graph will go. Number 3. Is there a vertical asymptote? No. Now that's creepy, right? Because it's ln. It has a vertical asymptote, but what happened? So, see that x squared plus 1, right? If it was just x squared, then it would still have a vertical asymptote. This plus 1 killed the asymptote because there's no way to make a 0, right? ln of 0 is what produces an asymptote. So if you want to find the vertical asymptote for Ln, you would have to take the argument and set it equal to 0. But that has no solution, so there is no vertical asymptote. We have no ha and no sa either. They don't have them anyway for Ln. So the way to get the asymptote for Ln problems is to take the argument and set it equal to 0. But in this case, setting equal to 0 did not produce any x values. So no asymptotes of any kind. All right. Number 4 is our f prime derivative. And we love these derivatives with Ln functions because you get to write denominator as is and then its derivative on top. Right? So it was as easy as that. And then for the second derivative, we'll have to bleed a little bit. It's a quotient rule. Or you can do the logarithmic differentiation because that will even do better. 2x x squared plus 1. And then the second part over here is in the numerator, we just have a 2 and then 1 over x. And then minus the denominator would be x squared plus 1 with a 2x on top. So these are my two derivatives. You can also do quotient rule if you like it. It's whatever. I'm gonna get the same eventually. I like the logarithmic because it gives me the factored form. I can just set each one to 0 and be done. First derivative test. I take 2x over x squared plus 1 and I set that equal to 0. Now, before you run, remember that when you cross multiply, the denominator dies. So you're just looking at 2x equals 0, sec equals 0. We already had that. 0, 0 is a point for us already. So it's x and y intercept, and at the same time it's going to be a critical point, which is awesome. Right? So we already have that 0, 0 there, and we're just going to add a min or a max or inflection next to it when we get to it. It's going to be something, right? So now, my partition. Remember, we have all real numbers on the domain, and only one critical point at 0. There are no vertical asymptotes. I create two test points, -1 and 1, and then I start working on my first derivative test, -1. So that's going to be 2 times -1 divided by, I don't even have to write the denominator because the denominator is always positive. We established that already, right? X squared gives you always a positive number plus 1, so it's always positive. So what I have is a negative divided by a positive, which is negative. We don't care what numbers we're getting. So it's decreasing as we are going. Now, guys, on the other side, you can get another decrease, in which case this becomes inflection point, or you can get increase, in which case it becomes a minimum. Right? Those are the two options. There's no third option. It's either going to be increase or decrease. So as soon as I calculate f prime of 1, which is going to be 2 times 1 over positive number, which is positive over positive, which is positive, it's increase. So now we know it's a minimum. Such an awesome, quick, smooth calculation, right? Well, okay, now we have a inflection point to make up for it. So, second derivative test, 2x over x squared plus 1 times 2 over x minus 2x over x squared plus 1. Equal to 0. Now the first calculation here is going to give us that x is equal to 0, but we have to drop it because we know that it's a minimum. Can be inflection point at the same time. The second part, 2 over x equals 2x over x squared plus 1, is the one that we have to compute. Cross multiply, we get 2x squared plus 2 is equal to 2x squared. These drop, and I get 2 equal to 0, which cannot be. So I have no values to partition on, just have one partition. I don't like this. I don't like it because 0 is a minimum. We calculated that. But now this thing is telling me that the 0 is the inflection point at the same time, and it cannot be. I don't like it. This part gave me nothing. Did anyone do quotient rule? Do we have the same answer? X squared plus 1, everything squared, divide over here, x squared plus 1 times the derivative of the top, which is 2, minus 2x times 2x. That's a 4, no. It is 2x squared
minus 4x
plus 2 minus 4x squared equal to 0. That's a 2 times negative 2x squared. Negative 2x squared plus 2. So why is this thing? What did I do wrong? Because I'm getting plus minus 1 now. Right? I did something wrong. Why is my derivative wrong? You copy the function as is. You have 2x. So that's going to be... Oh. No, there's no 2 there. Because that's going to be a 2x and a 2 on the top. And then they cancel. There we go. If it's x squared, would be what I had. Holy nightmare. Holy nightmare, Batman. So this is now 1 over x. Now, that's 1 over x. And that changes things over here. That changes things. So how do they change? We have 1 times x, so that's x squared, and that's a 1. And that's when you cross multiply 2x. So when you move this to the other side, you get that x squared is equal to 1, from where x is equal to plus minus 1. Ha! So we partition at negative 1 and 1 and at 0. So I have negative 2, negative 1/2, positive 1/2, and 2. Alright, so let's go. Yeah, I'm gonna regret this. But such is life. So f double prime of negative 2 is going to be 2 times negative 2 divided by negative 2 squared plus 1 and in the bracket 1 over negative 2 minus 2 times negative 2 divided by negative 2 squared plus 1. Perfect. This is equal to negative 4 over 5. In parentheses, I have negative 1/2. Minus and minus will give me plus 4 over 5. What's bigger, 4 over 5 or half? 4 over 5 is bigger. Negative times positive is negative. So less than 0. So decreasing here. Now we got to do the same thing for a half. F double prime negative 1/2 is equal to 2 times negative 1/2 divided by negative 1/2 squared plus 1 open bracket 1 divided by negative 1/2 minus 2 times negative 1/2 divided by negative 1/2 squared plus 1 close bracket. I hope you got that.
Are we redoing the first derivative test?
No, this is the second derivative test. Right? Second derivative test.
But doesn't that tell you if it's
concave
again?
Oh. It's time to end class and go home.
I agree.
But then there is the review.
Oh no, we can hang out all night.
Yeah, see, there you go. So, yeah. Such is life, right? This is negative 1 over a quarter, so that's a 5 quarters, so 4/5 over here. Great. And then we have negative 2 minus negative 1 divided by, again, this is 4/5. All right, fine. So that's going to be a plus, but negative 2 is a negative, negative. That's a positive, right? I mean, negative times. Yes, this is a positive, so I can kill that minus and put a positive there. So negative 2 is still bigger, so that's negative times negative is a positive. So another concave up. No, concave up now. There we go. Now I get to do it all again. Oh, I just need to kill negative signs on. Right? So this is what you do. You circle your equation, then you go here, you push the button, you push paste, move this box, and you put it right there, and then you just kill the negative signs. Easy, right? And what do I do then? This is going to be 1 over, and this is now 4, 5 over 4, so 4/5, and then open brackets, this is a 2, minus, that's a 1, and it's again 4 over 5. 2 is bigger, so positive and positive concave up again. Concave up. Well, we better have a concave up because we have a minimum at 0, right? Do we? Yeah, we do. There's a minimum at 0, so you better be concave up over 0. Otherwise, doom. And finally, we have this one with a positive 2 everywhere. Copy. Let's go over here. Bring that there. Kill all the negatives. And calculate. That's going to be a 4 over 5 parenthesis 1/2 minus 4/5. So that's a positive times a negative equals a negative, and that's a concave down. Spicy, huh? Awesome. Can we make this worse? Of course. All right, we can. That was a one good second derivative test. So now we draw a graph. And what do? Well, we know 0, 0 is the minimum, so it gets a smiley face right there. Now, what else do I have? And I think the answer is nothing. Yes, the answer is nothing. After 20 minutes of work, I have nothing. Right? I have only 0, 0 point, which serves as everything, X and Y-intercept and the minimum. I have no vertical asymptotes for guidance whatsoever. No vertical, no horizontal, no slant. Right? The derivatives were just, you know, floating about these things. So what should we do? This is where we calculate extra points. There's nothing else we can do. So we compute additional points so we can graph. So what is original f at 1? What our original function, wasn't it ln plus 1? ln x squared plus 1 is just ln of 2. Great. F of 2 is ln of 2 squared plus 1 is equal to ln 5. Going on through these. So I have a point 1 ln 2, I have a point 2 ln 5, and it's gonna go like that. So prediction over here, because there are now, oh, we have changes in concavity, guys. We have changes in concavity at -1 and 1. No one said anything. Right here. I should have boxed these things. Need to find their y values. Well, we found y value for 1. Now I just need to find the -1, which is the same. And the title for these ones will be get y values for inflection points, and these over here are inflection points. So I have 1 ln 2, so I'll just put there and there. So now that does look like a smiley. Look at that. So I connect them like this, and then we have to branch out. How can I tell? This piece over here has to be concave up. These pieces have to be concave down because of the second derivative test. That's how I tell. I also see a decrease into the minimum and increase after the minimum. Are we all bueno on that? Good.
Why is there no horizontal asymptote?
No horizontal asymptote. This is going to grow forever. The bigger the x, the bigger the y. So it's not bounded on top. It's not going to follow any value. Just like, remember that x squared has no horizontal asymptote? It just goes up forever.
Yeah, but I feel like, because like when I think it's, I forget which one it is, but just looks like it has one.
But it doesn't. I know. It's heartbreaking, but such is life. And now we go to our friend Desmos over here. Ask ln of x squared plus 1. And there it is. Oh. You can't see it. I got excited. And you can see your change in inflection points, right? Where this piece is concave up, and then these pieces, like the wings, are concave down. That's that. One more example. Okay, 2, fine. Okay. Oh. I actually kind of want to do 2, but then should we do break and then do 2 and then do the... Yeah, let's go for a break. And when we come back, we'll have a part 2, the revenge on graphing functions.